Recording is rolling. It is Friday, September 23rd. You guys remember yesterday you did the Atwood lab, and then a couple days before that, we were looking at free-body diagrams. So I'm going to pick up from there, debrief the lab with you guys, show you guys the solutions, and then you guys are going to see how close your formula was to the textbook answer. I'd like to also hit some college physics textbook problems. We still have to finish the Bird-Peter problem, so I want to go back, hit that. And then there are a bunch of Atwood related type questions that I'd like to hit before the weekend. Okay. Next week, got some fun stuff coming up. You guys remember you're going to finish AP Classroom Unit 2 before you show up to class Monday, right? So we can take Monday and go over those, right? Right, you guys do that? So that's your plan, right? I think a couple of you guys have already submitted that. Right, then I need to finish this college physics problems with you guys, but I do have a bunch more labs and lab type activities lined up. So the big one's going to be friction, but I have a few other ones too. At some point, I'd like to slip in an FRQ and some other things if I can. So might be able to squeeze all that in next week. We'll see. And then after that, we'll be off to the section after this is going to involve centripetal force, like circular type motion, combined with gravitation, and you can put those two together, make orbit. So that'll be like after next week. All right, let's get going on Atwood. So you guys did these two setups yesterday. You did a few combinations of these, a few combinations of these. I realized after you guys left, I actually forgot to put out scissors. So I don't know how you guys got the string, but somehow, yeah, some kind of magic. So what's remember what you're trying to figure out? What's the acceleration of the system as a function of these input masses? Well, that's maybe a different way to phrase that. The more technical way to phrase that is like, what's the downward acceleration of the heavier weight, right? That might be how you think. Right, so go solve this from a free body diagrams point of view. Just gonna copy this picture right here. We got this going on. Okay, let's put a heavy one up here. I'll call this maybe M2 could be the heavy one, I guess, right? And M1 could be the small one. Although you can do either way. Right, I guess mine's gonna go clockwise, but one way or another, gonna go clockwise or counterclockwise. Right? So put a center mass dot on each one. Right? And let's think about what forces are going on. So we're technically doing two free body diagrams, right? One for each mass. Okay? So this one definitely has a weight pulling down. I'll call this the weight of M2. So it's M2G, right? Mass times gravity field. Thank you. And then similar story on the small one. Okay. Now, so this one's definitely going to be a shorter magnitude weight, right? Right. Now, actually, if I just stop there, those are the external forces that are driving the system to move, either clockwise or possibly counterclockwise, and just swap the masses, right? Is that right? So actually, that would be enough to solve it. But if I go back and put in some more details, I shouldn't have like a tension force. Okay. And shouldn't that tension force be equal on both of them? But it's also like the Goldilocks force, right? It's larger than the small weight, but it's smaller than the big weight. So that it can drive the small weight upwards at the same time that there's a net force downwards on the big weight. Right? So I'll do F sub T, tension force. Okay. You guys saw all this a couple of days back. Okay. Just a reminder, right? Okay. There's also some forces up the pulley, you're holding it. I'm gonna just ignore those altogether. Okay. Right. Now, at this point, there's different ways you can approach this and set this up. Some textbooks and teachers, the way they go about it is they look at each free body diagram and set up a system of equations, and it goes through the tension force, blah, blah, blah. Okay. There's a different way I like to go about it. I'm just going to teach you guys a different way. If you're really curious and want to see all the different ways, then the internet is vast and full of information. But I'm going to show you guys a macro point of view, right? Which is I'm going to treat this like a tug of war. Like you guys play tug of war, right, with the rope. And this is essentially that, except it's just wound around a pulley, but otherwise think of it like that. Okay, I'm going to look at from a macro point of view and say that this whole tension force is just internal. Okay, so we can go back and solve for it later, but I'm going to figure out what the acceleration of the system is first, okay, and then worry about the tension later, if I care about that, okay, which you guys didn't on your lab, but it could come up in a textbook context. Okay, so I'm going to say net force. That's the sum of forces is the net force, right? Net force. Is equal to M total times acceleration of the system, right? So maximum acceleration, or if you like, Actually, I prefer Newton's second law of motion written this way. The acceleration of the system is caused by a net force acting on a total mass, right? That's sigma f, that's the sum of forces. I guess give you sum of forces, sum of masses. Okay. Now, forces, you guys know, it's a vector quantity, so these might be subtracting from each other because one say let's go clockwise, one says counterclockwise. But the masses, that's a scalar, so you only ever add up the masses. Okay. What does that mean? That means the acceleration is going to be, well, net force should be, these two guys are what are fighting each other, right? M2G and M1G. So should I do the difference between those two? Exactly. The difference in weights, M2G minus M1G, right, would be the net force. Okay. Right, now pause right here. Think about why that would make sense. Remember we established the boundary conditions, just thinking about it before you guys even got your hands on the materials. Saying, well, if these were the same, it should balance out. Okay. In fact, you guys test that. You get that. You put 200 grams, 200 grams, it didn't need to move, right? Because it would subtract out, wouldn't it? So that is consistent with what we were thinking, what you guys saw. Okay. And then divide by, okay, so that's the net, just the net force, right? Now, isn't that driving both of these masses to move? Both of these masses have inertia. So shouldn't I just add those up, like M1 plus M2, or you could say M2 plus M1, either way, right? Okay. The sum of masses, that's the sum of the masses, right? You guys got that? Okay. And actually, this right here is the answer. That's a perfectly valid answer. Okay. But you can do one little tweak to make it look exactly like what you probably got on your page if you got the answer right. I could factor out that G, couldn't I? Right? If I want to, I could say the acceleration is the difference of masses over the sum of the masses of gravity. Right? So this is a valid answer. This is the same thing, just slightly differently written. Okay, that's it. Yeah.
When you're calculating the net force, could you include the tension force?
Okay. Now tension is just internal to the system. Okay. I think the example I used the other day is like this pen. Right. If I have if I push on it with my hand, or say I'm like rolling it around, right, I'm definitely applying an external force to the pen from my hand. It's coming from my hand. There's an external force. Okay. So what's moving like this little particle right here? Okay. Well, there's like some plastic bonds in the pen that's just holding it together, right? So that's not an external force driving the pen to move, right? That's just an internal force like holding this object together, right? So similar idea here, that the tension is just holding the outlet together. Okay. Right now, what you can do is you can take this, and once you know the acceleration, see one's accelerating down, one's accelerating up, right? So I guess they have like directions on those individually. Then you can focus on the free body diagram for either one mass or the other mass. And then you can solve for the tension that way. In fact, I'll do that with you guys. I'm going to pull a textbook problem, one of your college physics problems. We'll do that. So we'll go a step deeper with that problem, and we'll go solve for that tension. Okay? You guys got that? Okay. So hang on to that idea. Okay. Let me see, show of hands. How many guys got that? How many guys got the answer on your lab? How many guys got that? Ooh, all right. Okay, because remember, here, take a look at the goal, right? So there's your Atwood setup, your classic double elevator Atwood. Says find the relationship among the actual acceleration, which was this last column, you found empirically, free fall gravity, 980 centimeters per second squared, and mass 1 and mass 2 using the starred columns. Remember I told you guys you could take just pure free fall G, the difference in masses, sum of the masses, somehow multiply and divide those to get A, right? And look at that. That's exactly what it is. It's the difference over the sum of the masses times free fall gravity of the planet, right? In fact, if you run your numbers, I bet it's probably not exactly that, because there's a little bit of friction that throws everything a little out of whack, but it's probably pretty close, right? Probably better than anything else, right? Guys got that? Okay. And then here's your second setup. Looks like this, or this one, right? Usually it's called like a modified Atwood. Okay. All right, so it's going to be a really similar story. All right, we're going to go. Okay. Have stuff like this. You put these hash marks to say there's something solid there. I got a pulley. Okay. Yeah, remember a good way to do this was to put a big old mass here. Maybe I'll call it like M2. Okay, throw it on a Hot Wheels car, just get rid of the friction. Okay. And then let's see, got this tension here, right? And then this M1, right, which was hanging down. Okay. Okay, now this one, there's one force that was especially important, and that's the weight of M1, because that is the external force driving the system. So I'll call it M1G. Okay. Now, are there some other forces? Yeah, there's this tension, which is going to be necessarily less than the weight of M1. So the tension force and the exact same tension force right here. What should be center mass dot F sub T there. Okay. Of course, M2 had its own weight, but that didn't matter because it was being balanced out by the normal force. Right. So these two just cancel out anyway. Right. And the hotless car pretty well got rid of the friction, so it was called friction negligible. Right? And the tension force is just internal to the system. See, if I'm looking at this from a systems point of view, from a macro point of view, then the only force I really care about is the weight of M1. Again, you could approach this from a different point of view and do, but I'll just do it this way, and then you guys see this work out. All right, so I got what's the acceleration system? Well, it's the net force on the total mass that's being moved around. Okay? And the net force is just the weight of M1 that's hanging down here, M1G. Okay. And the total mass is M1 plus M2. That's it. That's the whole thing. Okay, that's the answer. Right? Newton's second law of motion. Net force, which is just this guy, acting on this much mass, this much inertia. Right? Okay. You guys got that? It's like a two-step proof. Boom, boom. Is that okay? All right. So can I do this? Hang on to this page only because on the opposite side, I did print you guys some very convenient tables to do a two-part friction lab that I'm gonna have you guys do tomorrow. And then I will have you guys do a full AP write-up for, well, one of these. Here's what we'll do next week. I'll have you guys do both of these and then just pick your favorite version of solving for coefficient friction and do an AP style right up to that. But that'll be next week's adventure. All right, so you guys ready to move on? Next thing, any questions? All right, so let's take a look at some college physics questions here. Right now, I know. Do you want to finish the Bird Creek one, but not right yet because we're still in the since we just did some Atwood, we were thinking about Atwoods. Let me go ahead and knock out some Atwood problems because there is an additional question with these, which is what is the tension in the string? So I want to take you guys through that just with numbers, right? Not solve in terms of variables, but actually do the numbers. Okay. So number 38, you see number 38? Hey, look, that's your classic double elevator Atwood. And one right before it, number 36. Ooh, that's the modified. So people can knock out both of those. All right, two objects, and they give you a couple of masses. Maybe for the notes, I'll change the masses so you guys get more independent practice. Are connected by a light string over a frictionless pulley. And notice they said to find the tension first and the acceleration system second. And I'm going to do this in reverse because just the way I like to solve these. Okay. And then, and the distance each object will move in 1 second. Ooh, that sounds very kinematic, doesn't it? If they give you a time interval, it starts from rest, and you know the acceleration has 3 kinematic values, you can solve for how far they move. Huh, interesting, right? All right, so we're back to double elevator Atwood, which is, well, there we go. It's right here, right? Okay. Okay. So let's suppose that, here, maybe I'll break out the pink and just throw some numbers in here. Let's call mass 1, how about 7 kilograms, and mass 2 could be like 8 kilograms. How about that? Okay. See how they're kind of close in value to each other, but there's definitely an imbalance, right? Okay, so I'm going to run these numbers and then show you guys all the points that they're making about these Atwoods. Right, so we got 7 and 8. Is that okay? Okay. Now I've solved it in terms of variables already. Right here, how's that going to look just with the numbers? Right, I mean it's going to be pretty well the same thing. Okay, we got the acceleration of the system is the net force on the total mass. Okay, and from a systems point of view, the net force is it here? What's the weight of this guy approximately in newtons? What's 8 times 10? 80 newtons, right? 8 times 10 is 80 newtons. So it wouldn't be an 80 Newton force minus the 70 Newton force. Right, you guys get that? Because M1G is 70 newtons. It's 7 times 10. You can just plug it into those, right? 70 newtons. Right, so I got a net force of 10 newtons, right? It's like two guys playing tug of war, and that's the difference in the forces. Driving, how much mass? 15 kilograms. You guys see 15 kilograms, right? 8 kg plus 7 kg, right? So see the forces, you take a difference because they're pulling opposite ways and force is a vector quantity. But the masses, it's always going to add because mass is a scalar, right? You just keep adding up all the masses. And that's how much total inertia is being moved around. So I've got 10 Newton net force acting on 15 total kilograms. Oh, yeah. Actually, I do specifically want to keep kilograms because kilogram is the base unit. Like, you guys remember 1 Newton is 1 Newton is equal to 1 kilogram meter per second squared. Like, kilogram is an ingredient that's baked in the cake, right? So that when I take newtons divided by kilograms, that's going to leave me just meters per second squared, right? So actually Newton per kilogram, that's an alternate way to express acceleration, right? Force on mass, it's from a dynamics point of view. So sometimes even AP, you'll see that. Like here, I know this is kind of a tangential thought, but you guys know how gravity on Earth is, well, here, how about this, 9.8, say equals 9.8 meters per second squared. Sometimes you actually see it in dynamics units, 9.8 Newton per kilogram. Okay, that's the same thing. Okay. Yeah, so I definitely want kilograms if I can keep kilograms. Okay. Now you guys yesterday lab masses, those were in grams. That's okay, but if I want calculations, I want kilograms. Right, so I'm getting about 2/3 of a meter per second squared. That's what that would be, right? About 0.67 meters per second squared. Sorry, 0.67 meters per second squared. Okay. And hopefully that kind of makes sense because those are pretty close in value. So the acceleration would be pretty slow. Remember the boundary conditions are, if they're exactly the same, it's going to be 0 acceleration. If you put all the weight on one side, it's approaching 10 meters per second squared, right? So in fact, they're kind of close to each other. It's closer to the 0 end than the 10 meters per second squared end, right? Is that okay? Okay. All right, so now I've got acceleration. I'm going to go the other step and figure out what is the tension? What is the tension? Now, you guys probably already here could make an estimate what the answer is going to be. Do you think it's going to be larger than 70 newtons, but smaller than 80 newtons? Do you guys think? Right, it's going to be between 70 and 80, right? Because the whole deal about being the Goldilocks force and the whole deal, right? Right. I bet if we we can focus on either mass. We can do M1 or M2. Maybe I'll just pick M2. Why not? I'm going to pick M2, and I'll do it from that point of view. So I'm just going to focus on this one, okay? And then solve the tension doing that. Okay, so here we go. So I'm just focused on M2, which is 8 kilograms. Okay, I know that there's 80 newtons pulling down. Of course there is, because that's its weight, 80 newtons. Okay, and there's some tension pulling up. I'll call it F sub T. I don't know what that tension is, but I'm gonna guess it's somewhere between 70 and 80 newtons, right? I don't know, maybe 75, something like that. Okay. Okay. Now let's kick back over to Newton's second law of motion. Net force is equal to mass times acceleration. Right? Except we're going to play it differently. Instead of from a systems point of view, we're just honed in on one of the masses. Right? Right. Hey, wouldn't the net force be the difference between these two forces? That's how we can ultimately solve for tension force, right? Because now it's going to be in the expression. Right? So the difference between 80 newtons acting downwards and the tension force acting upwards is going to result in this mass of 8 kilograms accelerating at how much? What's the acceleration? This many meters per second squared. We figured that out from a systems point of view. Right? We already know the acceleration block. Right? Now we're saying what forces are leading to that acceleration, right? Right? So isn't this like 2/3 of a meter per second squared, which we got from before? Is that okay? Right. Yeah. Right here, kilogram meter per second squared. That's newtons, right? Yeah, there you go. So we got that in newtons right here. So it's 8 times 2/3. So this is like 5.33 newtons. So 80 newtons minus the tension force is equal to 5.33 newtons, right? Newtons. All right. So can I add this over, subtract that over? The tension force, little algebra swap here. It's gonna be 80 newtons minus 5.33 newtons. Is that true? I'm looking at tension force is 74.7 newtons. Hey, remember, I'm rounding a little bit. Okay. Remember, we were trying to guess beforehand. We said, well, it's got to be between 70 and 80. That's the only thing that makes sense. Okay, maybe 75. Oh, it's really close to 75. Not exactly 75, but pretty close. Okay, that check out. Okay, so here you go. Let me take you airplane view over this whole problem that we just did, because it's like a multi-part complex problem. Okay, start out just knowing a couple of masses, right? Actually solve this in terms of variables too, right? But what if you have some numbers? So this many kilograms, this many kilograms. Well, that means they each have a weight. If they each have a weight, you can find the net force driving the system to move, right? Clockwise, counterclockwise. Net force on total mass gives you acceleration of the system, right? Well, that's the way I would say it. It might say like, this is the downward acceleration of the heavy one and the upward acceleration of the light one, right? Right. Once you know how it's accelerating, you can set up a separate force equals mass times acceleration, Newton's second law, but just for a single block, not for the whole system, but just for a single block. And then say the net force is the difference between the two forces on it, and then use that to solve for the tension, knowing what the acceleration is, right? Okay. Again, there's another way to set this up where you actually solve for the tension first and acceleration later, but okay, I always just teach it this way. Okay. That's good. Everett? All right, let's take a look at there's some more Atwoods here. Here's a modified Atwood here. Okay. And there's even one with an incline. I really want to do this one with you guys too, but we got limited time, so I'll see what I can do. Let's do a modified, and then we'll hit the bird feeder, and we'll see where we are in terms of time. Okay. Okay, well, here's the modified setup. It's solved in terms of variables already. Here, I'll just take my peaking out and tag some masses. Hey, let's make M1 really small. Let's call this guy like 1 kilogram, 1 kg. Right? And let's make M2 really big. Let's call this guy like 9 kilograms. No. Let's do 8. Let's do 8. Okay. 8 kilograms. Okay. 1 kilogram versus 8 kilograms. Should that accelerate kind of slowly? Okay. Let's finish out the numbers right here, because we got some space here. Got all in terms of variables already. So the acceleration is, well, the net force is the weight of this 1 kilogram. So how many newtons? Guys, what's 1 times 10? It's a 10 Newton weight, right? So you got 10 newtons of weight acting on how much total mass? 9 kilograms, right? So isn't that 1 kg plus 8 kg is 9 kilograms? Hey, newtons per kilogram. That's the same thing as meters per second squared. So what is 10 over 9? That's 1.11. Acceleration is 1.11 meter per second squared. Boom. So that's specific to those numbers. All right, retire that peak pen. I got more peak pens. Okay. Is that okay? Okay. Okay. Okay, and then let's go to the extra step of figuring out what's the tension. Now, you could pick either block and solve for the tension, and you're going to get the same tension, whichever perspective you do. I'm just going to pick one and go with it. Let's say the one that's hanging down. Okay. If you want to check this later, you can. So the one's hanging down. I got mass 1 is 1 kilogram. It has a weight acting down of pretty close to 10 newtons. I'll call it 10 newtons. Okay. And it's got some tension force, F sub T, pulling it back. Now, I'm going to say, since this is accelerating really slowly, that tension force is probably pretty close to 10 newtons, but a little bit less. I don't know, maybe close to 9 newtons. I'm just going to guess before we start this problem. Maybe about 9 newtons. Okay. Okay. Let's see. So I'll set up Newton's second law of motion. Net force is equal to mass times acceleration. Okay. Now here, the net force is the difference between these two. Let's call it down positive, just like I did that for the last one too. 10 newtons down minus the tension force up is going to result in this 1 kilogram block accelerating at a value that we already figured out. Remember, we figured out it's 1.11 meters per second squared. Okay, you guys know that? Okay, from, that's right here, right? Okay. All right, so then do a little algebra swap. I'm gonna get tension force is equal to 10 newtons plus 1.11 newtons. Hold on a minute. No. It is minus. Oops. Yeah, got my sign fixed up. Here, minus, right? That's 10 minus 1.11. That's tension force is 8.89 newtons. Right? And that could pretty well make sense, right? If it's 10 newtons down, 8.89 newtons up, that's a very small net force, which means it's going to accelerate slowly, right? Which is consistent with a small weight pulling a very large mass. Okay. All right, is that okay? Oh, yeah.
I don't
That was true for the double elevator. Okay. For the double elevator, you do need the difference in masses or the sum of mass. Well, the algebra works that way, difference in masses over sum of masses times gravity. Okay. But for the single elevator, there was a little bit different answer. It was the only force that was acting as a net force was just the weight of M1, M1G, right? Yeah, so this is for a single elevator. Okay, so some sort of, I don't know if they fit on the same screen, but kind of side by side. See, they're a little bit different looking answers, right? Okay. You guys get it? Okay. So that this answer was difference over sum of masses times G. This one was just the weight of M1 divided by the sum of the masses. Okay. A little bit different answers. Okay. Everybody right? All right, let's go. I think I can at least finish this bird feeder before the bell rings on Friday. Okay. You guys okay? All good? All right, so I know this goes back a few days. You guys remember we got this far in the bird feeder problem? There's this bird feeder, it weighed so many newtons. I made up a number for the note so you have a little bit more independent practice. I called mine 250 newtons of weight. Okay. And then we were looking at these ropes holding it up, and they were at these angles, and we split those into components using, playing off this Cartesian system with these dashed lines. Okay. And we said, well, the right and left have to cancel out. That would satisfy this condition for equilibrium. Sum of forces is 0 along that axis. And also the vertical stuff has to also 0 out. So this component up, this plus this component up has to balance with this weight acting down. So that the force zeroes out vertically. Right. And then the bell rang on us a couple days back. Okay. All right. Got good? Now we can solve this with the system of equations. See how there are two unknowns? We don't know the tension on the left and the tension on the right. That's what we're trying to find out, right? What are those two tensions? Right. So there are definitely two unknowns. I bet I need two independent equations to set up to solve it. Right. Oh, and I sort of have two independent equations that are asking to be set up, right? One along each axis. Let's do it. Let's do the sum and forces in the x direction is 0. Therefore, I can set up the zeros out. Here. Tension on the left side times cosine 60 degrees. Let me just skip to the next step since we're short on time. Is that square root 3 over 2? No, it isn't. It's 1/2. Oops. Cosine 60 degrees is 1/2. Sorry. I'll go to this. Okay. Minus tension on the right side times root 3 over 2 has to be 0. Okay. So I don't know tension left. I don't know tension right. Okay. And then if I do the sum of the forces in the y direction is 0 newtons, I'm going to get, say, this up. So tension on the left side times sine of 60 degrees is root 3 over 2. Yeah, plus, right, this one. Tension on the right times 1/2. Okay. Minus 250 newtons is equal to 0. Minus 250 newtons to 0 newtons. Right? Now I got two equations, two unknowns. Is that okay? Okay. I went ahead and did the trig ratios. Right. Here's that. Right. Here's what I do. So I see a bunch of stuff being divided by 2. Is it okay if I multiply everything by 2? Okay. I'm just going to do a few little algebra tricks. There might be like 10 different ways to solve this, but I'm going to get rid of all the fractions just because it looks prettier. Okay. Get rid of all the fractions. So I can say this: tension on the left side minus root 3 times tension on the right side zeroes out. And also √3 tension on the left side. Plus tension on the right side. Equals, and if I had the 250 over and also multiply by 2, that would be like 500. Okay. Is that okay? Here's the system we're going to solve, right? Now you can solve with elimination or substitution. Those are just different processes. I do see a good opportunity for a substitution. Because, guys, can I take this, add over here, and get the tension on the left side is equal to √3 times the tension on the right side? Can I do that? Okay. And then take that and substitute it. Right there. Okay. Bring this down and rewrite that. So √3 times √3 times tension on the right side, plus another tension on the right side is equal to 500 newtons. Okay, I'm just doing some algebra. I'll keep a little fast pace here because we've got 90 seconds. Okay, so that's 3 times TR plus TR equals 500 newtons. Yeah, I can combine those, right? So I got 4 times tension on the right side is equal to 500 newtons. Divide both sides by 4. Yeah, thank you. 125. So tension on the right side is 125 newtons. That's right. Right. And then if you want to get tension on the left side, could you take this, just multiply by square root of 3, right? So what's 125 √3? Tension on the left side, therefore, would be 216 point something, or 67 newtons. All right, there you go. Actually, that does look correct. So we are good. We are good. All right. Okay, you guys good? All right. So yeah, next week, lots of lab activities lined up, and you guys are gonna do AP classroom before you walk in class on Monday, right? All right. So let's call that a wrap on Friday.